In this lecture, we are going to use an RNN for time series prediction. The previous lecture looked at how to use an autoregressive linear model for time series prediction. So in this lecture, our main goal is to ask the question, does an RNN do better? This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. As you know, most of this script is the same as what you saw previously. So first we do all our usual imports. Next we create our data, which is a sine wave with some optional noise. So here's the sine wave without noise. As with this last lecture, we're going to run this notebook twice, once without noise and once with noise, to see how the RNN performs. Next, we're going to create our dataset. This turns our problem into a supervised learning format where we have an n by t by d input and an n-length target. So I assume you already understand this loop, since it's the same as the last script. The only difference here is, at the end, we need to reshape x to be of shape n by t by d, where d is 1. In order to do this, we can call reshape -1 t1. So the -1 acts as a wildcard here, so it basically means make it whatever size is necessary, so that the second and third dimensions are t and 1. Next, we're going to set the device. Next, we're going to build our RNN model. Luckily, we saw all this in the last lecture, so this will just be a review. First, our simple RNN will inherit from nn.module. Inside the constructor, we're going to take in several arguments: the number of input features, the number of hidden units, the number of RNN layers, and the number of outputs. First, we assign these arguments to instance variables, d, m, k, and l, as per our conventions in this course. Next, we instantiate the RNN object. For the input size, we pass in d. For the hidden size, we pass in m. For the number of layers, we pass in l. For the nonlinearity, we pass in the rel u. And we also want to set the argument batch first equal to true. This is to make sure the RNN module uses the convention that the n dimension comes first. Next, we have our final dense layer of size m by k. Next, we have the forward function. As input, we take in x, a batch of sequences of shape n by t by d. Inside the function, we start by creating the initial hidden state h0, a tensor of zeros of shape L by N by M. This is because we'll have an initial hidden state for each RNN layer, each sample, and each hidden feature. Next, we pass in X and H0 into the RNN module, which returns us two sets of hidden states. We typically only want the first one, since it's indexed by time rather than indexed by the hidden layer. In this script, we're building a many-to-one RNN, and in this case, we only need the hidden state at the final time step. In order to obtain it, we're going to index the RNN output by -1 at the second dimension, which gives us back an array of size n by m. Finally, we pass this n by m value into our final hidden layer, which gives us an n by k output. Next, we instantiate our simple RNN and move the parameters to the GPU. Next, we create our loss and optimizer, the MSE loss and the atom optimizer. Now, I just want to mention this again since it's important. When we do our train test split, we don't want to just randomly pick samples across the entire time period for the validation set. The purpose of forecasting is to predict the future, and thus when you split up your data, your validation set should always be future data points, and the train set should only contain points before that. Next, we move the data to the GPU. Next, we train the model. Again, this is all stuff you've seen before, so there is no need to repeat it. Next, we plot our loss. All right, so that looks pretty good. Next, we do our one-step forecast. This is almost the same as our autoregressive example, except the shapes are a bit different. The important part of this is how we shape the input and how we retrieve the output. Since we would like the input to be of shape n by t by d, we reshape it to 1 by t by 1, since n is 1 and d is 1. When we retrieve the output, which is n by k, we have n equals 1 and k equals 1, so we index by 0, 0. So let's plot the predictions. And as expected, this looks pretty nice, but of course we know this can be misleading. So let's scroll down to the real multi-step forecast. So here we can see that our RNN with the default parameters does not perform as well. This is a very intriguing result. If you recall, the autoregressive linear model does this perfectly, and in fact, we proved that we could find the coefficients of an AR2 model analytically. So why does an RNN not perform as well? The answer is that an RNN has too much flexibility. This is just like how an ANN is more general than a CNN. But just because an ANN is more general and more flexible than a CNN, it does not mean that an ANN will perform better than a CNN. In fact, constraining the parameters of a CNN to be shared makes a CNN better. And we see the same theme here. An AR2 model would work best because that model actually perfectly fits the dataset. It's the correct model. An RNN model does not. It has too much flexibility and too many parameters. We say that it is over-parameterized. Although, as you'll see later, the flexibility of an RNN does allow it to do more powerful things that an AR model cannot. Next, we're going to go back and add some noise to this dataset so that it better mimics what you might find in the real world. So let's run all this again. So there's the data. Here's the loss per iteration. Here's the one-step forecast. So if we look at the one-step forecast, we can see that it looks pretty good, which is what we expect. But if we look at the multi-step forecast, it looks pretty terrible. So in fact, an RNN performs worse in this scenario. I should mention that sometimes when I run this, I see good results from the RNN, but generally speaking, the results are unpredictable. Sometimes it captures periodicity, and sometimes not. So it may suggest that more tuning would be required.